Hello, good afternoon. Uh, Thanks to sub0 for inviting us to speak about our experience building co-processors with Polkadot Chains. And thanks to all of you for attending, and to those of you watching live. My name is Prabhu Eshwarla. I'm the CTO for Turnover. So we've been building in the Polkadot space for over 3 years now, and on the mainnet for 2 years. We have built and we are maintaining two types of networks. The first is a substrate layer 1 chain, and also a TEE network. For the substrate chain, our domain focus is on data privacy, NFTs, and gaming. And in terms of the developer focus, we've built some pre-built functionality on the substrate chain, and our goal is to attract developers who don't know how to develop smart contracts directly, but they can use our prepackaged functionality and use JavaScript SDKs to access them and build decentralized applications. In addition, for some advanced developers, we also have a WASM contract layer, which they can use. Quite an active chain. We have over 700K on-chain events and 700 nodes, over 90 validators, so we're still a sovereign network, and lots of people securing the network through nominations. We're part of the Substrate Builder program, and also have undergone several audits, both as part of the SBP and also external audits. And for the privacy focus, basically we've built a key management solution that is a hybrid on-chain, off-chain solution, and that's where the T network comes in. And the focus of this talk today is the key management. The way we'll do the session, 3 parts. Basically, I'll talk about an introduction to co-processors. The term may be new to some of you. And spend the bulk of the time talking about our journey implementing the key management. And we can wrap it up with questions. But we can change the format. If you have questions in between, please feel free to stop me. So what are co-processors? They're a very old concept. So in the good old days, there was only CPUs with the arithmetic logical operations. And then there was a need for doing these more higher intensive compute for graphics, for gaming. And that's where separate co-processors were developed to perform these rendering of images and videos and some parallel computes also. But beyond that, GPUs emerged beyond the graphics arena, and there are co-processors developed, specialized pieces of processors developed for things like cryptography, encryption, decryption, for doing signal processing, video editing, advanced math, machine learning, and all that. Now, what does all this have to do with the space we are in, which is Web3? It's an analogy. You can look at any layer 1 chain as a CPU. The only difference is it's a lot more constrained in terms of the resources you can access. You have a finite number of computations or transactions you can have per block. The memory access is limited. The storage access is also slow and limited. It's a sandboxed environment. You can't talk to external systems. The speeds of read and write on the storage are much slower than what you'll get with normal file I/O or database I/O. So as you can see, there are a lot of restrictions in building on-chain applications, basically. Now, what this means is that the variety of applications you can build is very limited on-chain. And so what people started doing is that they said, okay, we need to build rich features, which we can't do on-chain. So let's say consumer NFT apps or DeFi, these applications started building functionality off-chain and only kept bare minimum what is needed on-chain, things like asset ownership or identity and stuff like that. The problem with this approach, the good thing about this approach is that it prioritizes the user experience. But the problem with this approach is that the users have to trust what you're doing in the off-chain component. And when you have a protocol that has a mix of on-chain and off-chain, then what happens is it's the responsibility of the protocol to assure the users that what is being performed off-chain has been done correctly. And that's what brings us to verifiable computing. Co-processors are a way by which you can execute a piece of code on either a custom hardware or specialized hardware, and you submit the results on-chain. But at the same time, along with the results, what you do is you also submit a proof of the computation, which can be verified, and that can be used by the rest of the smart contracts. That is the premise of coprocessors. In terms of technology, I'll classify coprocessors into three broad types. Whenever you talk of verifiable computing, the first thing that comes to mind is a zero-knowledge proof. So how it works is, from a smart contract or an on-chain logic, from a current block, you have very limited access to data. You don't see the whole history of the transactions. So what you can do is you can have a coprocessor that has access to the entire on-chain data, performs some aggregation, performs some analysis, and then you can, let's say you can run it on you can have a custom circuit, or you can have a general purpose VM like a RISC-0 or a SP1 that generates an execution trace and also generates a proof from it. Most likely something like a snark proof, which is succinct. And you can post that on-chain, and the verification is mostly constant time. So that is where the idea of bringing these coprocessors to the Web3 space started becoming popular, and ZK was clearly one of the enablers, especially over the last year. The tech has evolved so rapidly. The second type of technology you can use is the TEEs. Just to understand why and where TEEs came from, again, in the good old days, people used to run their own data centers. But when the cloud computing revolution came, people had to outsource their workloads to a third-party provider. And especially when you have a business where your competitive advantage relies on the algorithms and the data you use, like you're doing a high-frequency trading or some kind of financial applications. When you outsource these, there's no guarantee that the employees of these cloud computing providers won't see it. With privileged access, you can see what's going on. So to prevent that, the specialized processes were developed by these vendors, Intel, AMD, etc. So what they do is they allow you to load a piece of program along with the associated data into a secure area of the processor, specialized processor. Basically, it gives you isolation. One main distinction is that normally in the Web 2 world, the security and especially encryption technology focuses on two things. One is how do you, while data is in transit, how do you secure it? That's why you have all these TLS kinds of things. And then also, how do you secure it while at rest? You can encrypt data, store it on disk and stuff. But what they do not do is, while the data is being processed, right, how could you secure it? And that's where TE comes in. So even an owner of the machine, the TE virtual machine, or the administrator cannot actually view what's going on. You can't use debugging tools to inspect, memory regions. So that way, it gives you, in addition to ability to provide a verifiable computation, it also gives you some element of privacy. And that's the solution we chose to go with. The third type of coprocessors are a bit technical, but mostly economical, right? So the way it works is it starts with you have a layer 1 network, and you are securing the network using tokens that you stake, like DOT or ETH. And then came these DeFi protocols, liquid staking protocols, where you can stake and you get back a staked version of the token, which you can use in other DeFi protocols, like for providing collateral and stuff like that. So the same concept, you take those restaking tokens, and then you use that to secure off-chain services. You can secure bridges, oracles, stuff like that, and also a coprocessor. So the idea is the provider of these tokens, they are underwriting the risk. They're saying, you accept my computation because I'm securing it with this economic value. And if you don't think I'm doing the right value, you can slash me. So that's how these economic coprocessors work. So these are the three broad types of technologies we've looked at. There are, you can imagine other types of technologies, like you can have FHE, running computations on encrypted data, and you can also post those on-chain. But when we started the work, FHE wasn't evolved. So you can imagine in future newer types of tech being used. Quick look at the use cases in DeFi. Already there are many projects, especially in Ethereum, which have off-chained their order books and risk management features. You can, let's say in the wealth management space, you can dynamically reallocate your portfolios based on the changing market prices using a coprocessor. You can create newer types of orders. You can change the lending rates, interest rates for lending protocols, again, based on the market movements and stuff like that. Moving beyond DeFi, you can run custom ML models for doing training or for inferencing, and you can post the data on chain. In the area of rollups, basically there are several centralized components. You have the sequencers, aggregators. Most of them are run by the foundations themselves. They're not decentralized. So one way to quickly bring better trust assumptions is to run them in a coprocessor and submit a proof of what they're doing on chain. So it's less centralized. You can also use these in things like prediction markets, and you can create on-chain reputation systems wherein as a user, based on the transactions I perform in real time, you can recompute my scores, reputation scores, or credit scores, etc. Just an example of the kind of applications you can enable using coprocessors, which you cannot do just having pure on-chain logic, while being assured that whatever you do can be accepted and used on-chain. So that's the quick introduction to coprocessors, and especially on why we chose T coprocessors. And I'll especially compare it with the ZK. So both ZK and TE allow you to verify the integrity of the computations performed off-chain. But in addition, what TE does is it allows you to verify the integrity of the program that is performing the computation. For example, you can have let's say a prover, a custom circuit or a general purpose VM running as a coprocessor, but there is no guarantee that you can always modify the program. You can censor certain transactions and stuff like that. But when you run this in a TE, what you can do is you can take the program and take a measurement of it, and make sure that whenever a computation is submitted from the TE to the on-chain smart contract, you can verify the measurement of the program. So, and then you also verify the proof, basically. So that's one distinction. And also, you get privacy for free when you do these TE-based computations, especially when you have data to store. Even ZK, for example, when you want to prove provide a private witness, right, to a prover, it needs a way to store that private data somewhere and provide it securely. Again, you can use TEs for that. So that's the quick introduction to TEs, to coprocessors. Any questions so far? Okay. We'll now go into what we've done with decentralized key management. Let's talk of why the world needs a decentralized key management solution. Let's take the example of you have some piece of private data, and you want to securely store it, right? What are your options? The first option is that you hand it over to a tech app, like a password manager. You got this one password and stuff like that. The problem is you're trusting the provider to keep your data secure and allow you to access it, right? You can be censored. The company can shut down and go. And more importantly, even recently, popular password manager, which is LastPass, got hacked, which means all the data that was secured is being available publicly. So there is a big risk with a centralized solution. Second option is that what you can do is you can generate your own key pair, and you can encrypt the data and store it on, let's say, a Dropbox or S3 bucket or something. But again, the problem there is you are responsible for making sure the key is not lost. And also importantly, when you have to give access to that data to somebody else, what you have to do is you have to find a way to transmit those keys securely, which is not a scalable option. So that brings us to the third option, which is what we have envisaged and we've built, which is a chain custody. So the way it works is that you create some, you encrypt some data, but you hand over the keys under the control of a blockchain, which is what our solution does. The way it works is quickly the workflow is a user takes some data. The data can be a secret, it can be a private key, some image, audio, whatever it is, something that you want to secure. And so using the DApp built on a turnover network, basically, first of all, a key pair is generated. Using the public key, you encrypt that piece of media. And the encrypted data is stored on a solution like IPFS. You take the content ID of IPFS and then go and mint an NFT on-chain, on our substrate layer 1 chain. And once you do that, you can actually hand over the control of the private key to these trusted execution environments. And the way we do it is we don't just give the entire key to one machine. We actually use a threshold decryption algorithm, which is Shamir's secret. And we split those private key into multiple key shares, and each key share goes into one of these machines. So at a high level, this is how you store it. And when you as the owner wants to access the data, you go to the TE and you say, please give me back my key shares. And what the TEs do is they go and verify. First of all, you have to sign the message to request your key shares, even for accessing it. And then the TEs will go and verify on-chain whether I'm the rightful owner. And based on that, I'll be given access to my key shares. So that's the high-level view of how the workflow takes place. We had some very hard requirements. I want to quickly go through those for the key management system, because as you can imagine, a lot of questions come around the security, right, and the confidentiality of information. So the first requirement we had was that the unencrypted data can never leave the user's device. If I have a piece of data I want to secure, I want to make sure that it's encrypted before it leaves the device. So that is a hard requirement. We also may want to make sure that the entire key is not stored on any single server, for obvious reasons, fault tolerance reasons, and security reasons. Also, the communications between the DApp and the TEs and between TEs should be highly secure. The TEs themselves should be able to generate their identity within the enclaves and then register on blockchain. Otherwise, what happens is you can use the operator's identity to post some transactions, but the operator can misuse it, basically. There should be redundancy for backups and fault tolerance. We also wanted to make sure there is provision for both short-term key storage and long-term key storage, because there are different use cases, and it's important, especially as we think of aspects like side channel attacks, right, where you need access to a machine for long periods of time, and we want to discourage that as much as possible. So we have two types of storage for these keys. I mean, two types of key storage, yeah. Also, because we didn't want to run these in a centralized model, we wanted independent operators to come and run these nodes for us to store these key shares, and we need to incentivize them, which also means we need to be able to measure them. So we need a measurement system, we need an incentivizing system for rewards and penalties if they do something wrong. And also, basically we needed to protect from man-in-the-middle type attacks, where somebody can snoop in on my communication from the DApp to the TEs and kind of replay those attacks. So these were some of the high-level requirements we had. We looked at some alternative tech. First of all, we looked at ZK, but it was not suitable for the requirements we have, because ZK, it doesn't give us the. Here we have a need to store the key shares physically, and ZK is not the tech for that. We looked at MPC, but the problem is in MPC, each key share is held in different places, and our requirement was that we wanted to reassemble the keys in one place inside the user's wallet, and again, for that, MPC is not suitable. We also looked at something called proxy re-encryption, where let's say anytime you transfer your piece of encrypted data to somebody else, the whole keys everything is the data is re-encrypted. But we found that the user experience was less than optimal, and so we dropped that option. So in terms of the security model, when you talk of TEs, obviously it provides inherent security in terms of what I mentioned, the ability to isolate the program, ability for even privileged operators to not be able to access what is being computed, stuff like that. But on top of that, we built a multi-layered security model, because no security model can be perfect. So it's always a multi-layers of security that you look at to bring more assurance to users that their keys are safe. So we built this threshold decryption so that no single computer has the entire key. We also built this proof of availability, where from within the enclaves you can post data on chain confirming that you've received these key shares. If, for example, you have some private data that you put it on a marketplace for selling, how does the buyer know that the decryption keys are stored on the TEs? So you need confirmation from the enclaves that they've received the key shares, and that's where the proof of availability comes in. Authorization and ownership verification is done on chain. Also, for redundancy purposes, we have multiple clusters of enclaves backing each other up, and these have to communicate in a secure way, enclave-to-enclave communications, which is more peer-to-peer comms, basically. Also, the identity of the enclave should be generated within the enclave itself, so nobody can tamper with it. Also, in terms of the transit, right, data and transit between the dApps and the TEs, the TLS communications, let's say we have a Nginx proxy server which is running right outside the enclave. It's easy for the operator to gain access to those. So we decided to terminate the TLS within the enclaves itself for higher security. To prevent replay attacks, we have this authorization tokens and block expiry. So within a certain number of blocks, the request, after that it expires, so you can't replay them. Malicious code protection is offered because you can take a measurement of the code, and if you try to modify the code, you have a different measurement, and that will be rejected, basically. Also we have these bonding for economic security. So we have combination of crypto security, standard internet security, and economic security. That is part of all these. All our code is open source, audited by the best experts in the TE software space. And we also have an ongoing bug bounty program that anybody can utilize. Quickly, some attack vectors. So just to talk about, if you go through some of the attack scenarios, that'll help us understand what all these things that I spoke about mean. Let's start with the elephant in the room, which is the side channel attacks. Basically, side channel attacks are not an inherent vulnerability, right, of TEs. It's just the nature of any hardware system. So how it works is, you can, if you can try to detect high frequency noise or voltage fluctuations, based on that, the idea is you can extract some information from what's running inside the SGX processor, right? So to address this, we have two types of things to mitigate this. The first is a threshold decryption scheme, because to conduct these attacks, you basically need to have access to these machines, and you have to do for a longer term. You'll have to keep trying these out to get any meaningful information out of it. So the chances that if you store the key shares in one machine versus multiple machines, increases basically you have a better chance that these attacks will fail. So we have a distributed set of nodes running across cloud providers or infra providers across geographic locations, and they have to attack not just one machine but multiple machines to gain access to data. So by doing this, you're reducing the chances. And secondly, we also have these two types of storage. I mentioned what we call as secret NFTs and capsules. So secret NFTs are designed for, let's say you have an event like sub0. You want to issue your entry gate pass, right, as a QR code. And it's only valid for this event. After that, it doesn't matter. So these short-term storages, storage of keys, are less susceptible to these side channel attacks. When you look at these longer-term storage, where you want to keep your keys, access to assets on-chain, and transmit it to your family after you're not available and stuff like that. So we give the ability for the users to change the keys, rotate the keys as often as they want. So these are two ways by which we mitigate the side channel attacks. Malicious code I spoke about, making sure the operators cannot modify the enclave code and try to, let's say you send some data to the enclaves and they in turn send it to their backend, like some of the hardware wallets did recently without naming names. So you can't do all that with a TE solution. Operators cannot deny access to your keys because we have a measurement system, and if they do censoring, they will be slashed, basically. Nobody can get unauthorized access to keys because it's verified on-chain. Your ownership of this private data is recorded as an NFT on-chain, and only if you're the authorized owner signed with that key, you'll gain access to these key shares. Replay attacks with the block expiry and auth token. If there is a loss of key due to a machine crash, so we have these clusters of enclaves that back each other up in real time. They synchronize the keys. So even if one cluster goes down, the other cluster takes over and can service your requests for storing or retrieving keys. If the operator pretends to run a TE when they are running it on a general purpose processor, we can detect that because we do something called remote attestation. Whenever something is reported, when you communicate with the TE, you can verify that it's running on a genuine, Intel SGX processor. So that is done as part of every communication between enclaves, basically. Operators can't gain access to the TLS certs. I mentioned that. And in terms of defects in code, again, I spoke about the audits and the open source and the bug bounty. And T is reporting incorrect Oracle data saying, I have not received a key share. When they have received a key share, again, you can't do that because these enclaves generate identity from inside the enclaves, and you can't tamper with that, basically. And also, when you have the short-term storage of keys with these secret NFTs, let's say the buyer wants to make sure that the seller has not seen. For example, if I have tickets to a music concert, right? Once I've seen the QR key, the value of that NFT is lost. So to prevent that, we have the ability for the potential buyer to check whether somebody has accessed the key or not. So that way, you can be sure that the data has integrity. And in case the owner of the secret data, the NFT, is not available due to whatever health reasons, death reasons, you can set up transmission protocols and say that if under certain conditions you transfer ownership of this piece of encrypted data to another wallet, and that is something we've implemented as well. And if the operators just decide, they can't just come and leave the network as they choose, because we have a 3-month unbonding period. So that way, there's more stability in terms of keeping the key shares available to the users. So essentially, we built this stack which has got on top of the standard SGX hardware features. We built a decentralization layer. We built a crypto economic layer with bonding. There is verifiable integrity of the programs that are running with our MR enclave measurements, secure communications modules to talk between the dApps and the enclaves and between enclaves, built-in oracles for communicating from the co-processor to the blockchain. You can do configurable chain endpoints. You can configure which chains you connect to. That's important because you have to make sure what if the operator just changes the chain endpoint and connects to the wrong fork of the chain, right? It can lead to disastrous results. So even all those, we can detect changes to those. So what's next for us? Now that we've built this thing specifically for a key management solution, it's easy to expand this to deploy custom workloads. Also, ability to build multi-proof systems, like you can have, let's say, a ZK proof. Let's say you have a VM running a standard Rust code that can generate proof, but at the same time, you can run it inside a TE and also generate a TE proof. So you can be doubly sure that whatever you're performing in the co-processor is secure enough. We can also do ephemeral compute because these machines are quite expensive. So you can actually spin up machines on demand and deploy custom workloads, perform some tasks, and then release them. So you only do a pay-per-use kind of thing. So those things also are possible. And importantly, what a TE enables is private data. Let's say I spoke about TEs. Let's say FHE you have, or you have ZK, or any kind of computation you do. You want to, or you have an ML model where you want to train the model on some custom data. So you can do all that, using our same key management system. You can issue the data as an NFT, and then you can make sure that you delegate access to that ML model, and they can run the computation and give back the results on chain. So there's for more information. There's links are available. You can contact me on Twitter, Instagram, if any of you is interested in using the key management system or the TE technology for any of the substrate chains. Do feel free to reach out to us. So that's the end of my talk. If you have any comments or observations.
Are there any questions? Okay.
You mentioned that when the data is like encrypted, you mentioned like one where a ticket, so the buyer can check if the seller has viewed a ticket or whatever is encrypted. How does the buyer know whether the creator of the data like it doesn't keep a copy of the unencrypted data.
It doesn't keep a copy of the encrypted data, but it checks the access patterns. If somebody tried to access the data of that particular NFT, then that is recorded in the logs within the enclaves, and those logs are publicly queryable.
Well, I mean, the original creator. The original creator needs to have the unencrypted data that they encrypt before they put it up.
Oh, yeah. See, you can't avoid that. The original creator, like the issuer of sub0, right? They are the issuers of these tickets. Obviously, they will see it.
Oh.
But let's say somebody else buys from sub0 and tries to sell it to someone in a secondary market.
Okay.
That you can detect
So it's access after the first.
after the
sale.
first creation.
Yeah. Okay.
Right. It's a good question.
Okay, any more questions? So thank you, Prabhu. That's a wrap for sub0, the Polkadot Developer Conference 2024.
Thank you.